What's up, StudyBuds? This is your StudyBud Heil, and join us in today's trip to the infinitesimal yet infinite world of calculus. By the end of this video, you should be able to 1. Become familiar with the basic tenets of calculus, 2. Know where calculus can be applied, and last but not the least, have an insight on what the concept of limits is all about. What is calculus all about? We've heard it from somewhere that calculus is the most devilish math there is. But why does it always receive incisive flags? Let's try to see first the big picture of calculus. Some random guy who took a calculus course may give a quick and dirty definition of the subject as follows: a tedious field of math about tangents of and areas under curves. Sure, that doesn't give justice to the grandiose of the field. It is an understatement. But for our case in taking an introduction to basic calculus, let's keep that definition in mind. As we go along the course bit by bit, we, by our own senses, will inadvertently know the true definition of calculus. Anyway, tangents to and areas under curves. These are the basic problems that lay the foundations of calculus. How are we going to find the slope of line tangent to a point on a curve? How are we supposed to find the areas under curves? And why do we need to solve these? For one, solving these will help us understand more thoroughly what rates mean. We would be able to find not just average rates, but also rates at an instant. That means we could find not just the average speeds, but also instantaneous speeds. We could also find the maximum and minimum values of a function just by knowing the rate at which the values of the function is changing. Knowing the maximum and minimum values of functions help us in our day-to-day decision making. From what should be the length of a fence in order to maximize area, to the production level of MP3 players in order to maximize profit, to the radius of your trachea that will incur the greatest velocity of a cough. Calculus is pretty useful. Another, finding the area under a curve results in an immeasurable application, especially in the natural science. It helps us find areas and volumes of irregular figures, work done and fluid forces, and even the total distance traveled based on a velocity function. And here's the most astounding one. When used efficiently, calculus could help us model pandemics such as this COVID-19. In fact, the researchers from UP are using more advanced calculus plus statistical tools in making the predictions of the number of positive cases each month. But how do they do these? How can we calculate the rates and areas under curves with accuracy? The answer is what makes calculus different from algebra and other fields of mathematics. In calculus, we solve the problems presented before, which are seemingly impossible to solve, by using a very clever method, approximation. When confronted by problems such as finding the slope of a line tangent to a curve, the only thing that we can do is to approximate. If we now have an approximate, then we can further improve it by further approximations. If we do this infinitely many times, then we can find the accurate answer. We gained precision through approximation, and this process is called the paradox of precision through approximation. Calculus has so many paradoxes, but this paradox explains how calculus works. Let's try using this by revisiting Galileo's free fall experiment. Galileo found that the distance traveled by an object in free fall with negligible air resistance is defined by the time-dependent function y is equal to 16t squared in feet, or y is equal to 4.9t squared in meters. The equation will give us the distance traveled by the free-falling body after t seconds. After 1 second, the object has traveled 16 feet. After 2 seconds, the object has traveled a distance of 64 feet. But there's something about the object that we can get from the equation. It's the average speed in an interval. Remember that the average speed is defined by distance traveled over time elapsed, which is equal to change in y over change in t, that is equal to y sub 2 minus y sub 1 over t sub 2 minus t sub 1. So the average speed of the free-falling body during the first 2 seconds, that is the speed from t is equal to 0 to t is equal to 2, can be computed as 16 times 2 squared minus 16 times 0 squared all over by 2 minus 0, that is equal to 32 feet per second. Graphically, that is just the slope of the line that passes through these 2 points. Believe it or not, but you just had a first glance at one major concept of calculus, which is called the derivative. Anyway, the line that passes through these 2 points is a secant to the curve, since it crosses the curve more than once. Now let's try to find the speed in an interval of t is equal to 1 and t is equal to 2. So, 16 times 2 squared minus 16 times 1 squared all over by 2 minus 1 is equal to 48 feet per second. So basically, the speed is just function of t sub 2 minus function of t sub 1 all over by t sub 2 minus t sub 1. Now, let's try to find the rate of the ball at t is equal to 1. Wait, what? How can I find the speed if I am only given a point? We've been solving speeds in an interval, not a point. But don't worry, we can do this. Let's try first to make everything dependent on a point, and in this example, a t is equal to 1. If we let h be equal to t sub 2 minus t sub 1, then our equation will become function of t sub 2 minus function of t sub 1 all over by h. H is equal to t sub 2 minus t sub 1 can be written as t sub 2 equals t sub 1 plus h, and so we can make our equation function of t sub 1 plus h minus function of t sub 1 all over by h. For free fall, our equation will look like this. 16 times the square of t sub 1 plus h minus 16 times t sub 1 squared all over by h. Graphically, it will look like this. What then? How can we use this to find the rate at t is equal to 1? Simple. Try to make h as close to 0 as possible. As close to 0, but not equal to 0. Numerically, this is how it looks. If we push h towards 0 as much as we can, the speed keeps getting closer to, yes, 32. And that's basically the speed at t is equal to 1. Graphically, it will look like this. What can you notice? The second line became a tangent line. Let's find the slope of this tangent line from its graph. What's the slope? Yes, it's 32, and we have found the instantaneous speed of the free-falling body at t is equal to 1. We achieved that just by pushing h to get as close as possible to 0. And this is an example of the paradox of precision through approximation. Remember, as we push our h as close as possible to 0, the average speed also gets closer and closer to the number 32. And this number has a special name. It's called a limit. And that's what we'll be talking about in our next video. To recap, first, we've learned that the tangent and area problems were the impetus to the study of calculus. Second, the paradox of precision through approximation runs calculus as based also on our example. And last but not the least, if we keep pushing an independent variable in our equation, such as h, as close as possible to a certain number, but not equal to that number, we will see that the function in return also approaches a certain number, and that number is called limit. And that's it, StudyBuds. That's the end of today's video. I hope you had an intuition in how calculus works and what a limit is. This has been your StudyBud Heil, reminding you to study well. Till our next trip to the study world, toodaloo!